Welcome to Chapter 12, Introduction to Rings. So far in this course, we've talked about groups. We've done a lot of work investigating what we can tell about groups. Now we are ready to take this one step further to look at rings. And to get us an idea of what rings are, let's look at one example of something that is a ring, the integers, and see if we can generalize properties that the integers have under two operations, addition and multiplication. So let's see, what can we say about addition and multiplication of integers? What are some properties that those two operations on the set of integers have? Well, one thing that we could come up with is that both of them are associative and commutative, actually. So addition and multiplication both are those two things. So addition and multiplication both are associative and commutative. What other properties do they have that we've already encountered? Well, we have additive. The integers has an additive identity and it also has a multiplicative identity. So our additive identity that is 0. And then we also have a multiplicative identity. And that is 1. What else do we have? Do we have inverses? Well, we have inverses under addition. We don't necessarily have inverses under multiplication, but we do have additive inverses. And one thing that we haven't encountered yet, talking about groups, because we only had one operation available, we do have a property for working under addition and multiplication with inverses that combines both operations, and that is distributivity. We have distributivity. That means that when we have an A times B plus C in parentheses, we can distribute the A over the sum B plus C. So this is equal to AB plus AC. So those are some of the properties that the integers have under these operations, and we are going to generalize this example to define a ring. And so a ring is a non-empty set, we're going to use R for ring, with two binary operations, addition and multiplication, such that a bunch of things have to be true. So for elements A, B, C in our ring, we have A plus B is equal to B plus A. So we have commutativity. We also have A plus B plus C is equal to A plus B plus C. So that's associativity of addition. Then number 3, there's an element 0 in our ring such that A plus 0 is equal to A for all A in R. That is, we have an additive identity. And then number 4, there's an element minus A in R such that A plus minus A is equal to 0. So we have additive inverses. Now those 4 things put together tell us that R is an abelian group under addition. So those are all the properties that together tell us that R is an abelian group under addition. And then we have 2 more properties that have to do with multiplication. And so number 5 tells us that multiplication is associative. And then number 6 combines our 2 operations. It tells us that multiplication distributes over addition. So we have A times B plus C is AB plus AC. If we multiply from the right, or if we multiply from, when we multiply from the left, but we have the same property when we multiply from the right. So A plus C, that whole thing multiplied by A is BA plus CA. So when we do right multiplication, we have the same property. Note that there are a few things that don't have to be true about multiplication. For example, it's not an assumption for a ring that we have multiplicative inverses. So note, it's not an assumption. We have no assumption of multiplicative inverses. So inverses only have to be there for our operation of addition. Now let's look, we have a few more notes, things that I want to make sure we mention, and that is if multiplication is also commutative, then we call R a commutative ring. So addition is always commutative in a ring, but multiplication doesn't have to be. But if we do have it, then we call our ring commutative. And so Z was an example of a commutative ring. So Z is a commutative ring. But not all rings have to be commutative. Okay. Now, a unity or identity in a ring is a non-zero element that is an identity under multiplication. So there was nothing in our definition of a ring that said that we had an identity for our operation of multiplication, but if we do, then we call it unity. So in our ring of integers, we did have a multiplicative identity, 1, and so 1 is the unity or the unity element in Z. And again, not all rings have unities. We always have additive identities, but not necessarily multiplicative ones. Okay, and so if we move on to inverses, in an element A in a ring R, if it has a multiplicative inverse, then we call it a unit. So a unit of a ring is an element that has a multiplicative inverse, and we are using a to the minus 1 to denote such an inverse. Okay, so in Z, again, we do have a couple elements that are units because they have multiplicative inverses, and they are 1 and minus 1. They're the only ones. And so our notation says that then the inverse, the multiplicative inverse of 1, well, that's 1, and the multiplicative inverse of minus 1, that is minus 1. So they are both their own multiplicative inverses. Okay, what else do we have? If a ring has unity, then it's unique. And if a ring element has a multiplicative inverse, it's also unique. And that's actually theorem 12.2. And then just one note about general ring notation. We are going to use U0 to denote our additive identity. And we're using 1 for our unity element. Even if we are in rings that don't have integers or real numbers or rational numbers as entries, so even if we are looking at a ring of matrices or we are looking at a ring of polynomials, we are still going to use 0 to denote our additive identity and 1 as our unity element. We are going to use minus a to denote additive inverses. So minus a is the additive inverse of a, and then a to the negative 1 is the multiplicative inverse of a. And then finally, n times a means adding a together n times. So it looks like scalar multiplication, but it isn't necessarily. It means that you are taking A and adding A to itself n times. All right, so that was our definition of rings and a few notes about